Deep in the mountains of Boulder, Colorado, sits the most accurate clock ever built. It's so precise that it won't lose a second for 300 million years. But on July 19, 2020, this atomic masterpiece detected something impossible. Earth had spun faster than it should have. The day was 1.7 milliseconds shorter than normal. That's less time than it takes light to travel 300 miles. Yet this tiny difference sent shockwaves through the scientific community. Why? Because it meant our planet was breaking its own rules. Picture Earth as a massive spinning top. For millions of years, it has rotated at roughly the same speed. 24 hours per day, give or take a few milliseconds. But suddenly, our planet decided to speed up. The atomic clocks caught it red-handed. Dr. Sarah Martinez, a time specialist at the National Institute of Standards, remembers that moment clearly. She was reviewing data when the numbers made her pause. "I checked the instruments 3 times, she recalls. The clocks weren't wrong. Earth was spinning faster. This wasn't the first time our planet had surprised us. Earth's rotation has been gradually slowing down for millions of years, mainly due to the moon's gravitational pull. Scientists expected this trend to continue. But 2020 changed everything. The discovery revealed something profound about our home planet. Earth isn't the steady, predictable world we imagined. It's dynamic, constantly adjusting its spin like a figure skater pulling in her arms during a performance. These atomic clocks measure time using the vibrations of cesium atoms. They tick 9.2 billion times per second, with unwavering precision. When multiple atomic clocks around the world began showing the same strange results, scientists knew they were witnessing something remarkable. The implication struck immediately. If Earth was spinning faster, our carefully synchronized world of GPS satellites, computer networks, and international communications might need adjustments. The invisible foundation of modern life, precise timekeeping, was suddenly uncertain. But here's what made this discovery even more intriguing. Earth didn't just speed up once and stop. Throughout 2020 and 2021, it continued setting records. 28 of the shortest days ever recorded happened during this period. Our planet was clearly responding to something. The question became urgent. What force was powerful enough to change the rotation of an entire planet? The answer would lead scientists on a journey through melting glaciers, shifting ocean currents, and the hidden dynamics deep within Earth's core. This story begins with that impossible measurement in Boulder, but it reveals something much larger about our world. Every wave in the ocean, every gust of wind, every melting ice cube contributes to a planetary dance that's been ongoing for billions of years. We're just now learning the steps. The atomic clock that detected Earth's faster spin didn't just measure time. It opened a window into the secret life of our planet. What scientists found there would challenge everything we thought we knew about the ground beneath our feet and the sky above our heads. Your morning alarm goes off at exactly 7 a.m. You trust that 24 hours have passed since yesterday's alarm. But here's Earth's hidden secret. No 2 days are exactly the same length. Some are longer, some shorter. The difference is usually invisible, measured in milliseconds, but it's always there. Think of Earth as a figure skater performing on cosmic ice. When she pulls her arms close to her body, she spins faster. When she extends them, she slows down. Our planet does the same thing, except instead of arms, Earth redistributes its mass through melting ice, moving water, and shifting air. This revelation transforms how we see our world. Earth isn't a rigid ball spinning in space. It's a fluid, dynamic system where every movement affects everything else. The coffee you're drinking right now, the rain falling outside, even the air you're breathing, all play tiny roles in determining how fast our planet spins. Scientists call this the conservation of angular momentum. It's the same principle that makes a spinning ice skater speed up when she pulls in her arms. Earth follows this law perfectly, responding to every change in mass distribution by adjusting its rotation speed. Consider what happens when glaciers melt. Ice that was once locked at the poles flows into the oceans as water. This redistributes Earth's mass away from the axis of rotation, like the skater extending her arms. The result? Our planet spins slightly slower, but when water evaporates and returns to the poles as snow, Earth speeds up again. The atmosphere plays its own role in this cosmic dance. During winter, in the northern hemisphere, cold air becomes denser and sinks closer to Earth's surface. This brings mass nearer to the rotation axis, speeding up our planet's spin. Summer reverses this effect as warm air expands and rises, slowing rotation slightly. Even the tides contribute to Earth's changing spin. As the moon pulls on our oceans, it creates friction between moving water and the solid Earth below. This friction acts like a gentle brake, gradually slowing our rotation over millions of years. It's why dinosaurs experienced shorter days, about 21 hours long. But Earth's most dramatic rotational changes come from deep within the planet itself. Our core consists of molten iron spinning at its own rate. When this inner rotation shifts, it affects the solid Earth above, like two gears influencing each other's movement. Major earthquakes provide the most sudden changes to Earth's rotation. When massive amounts of rock shift during a quake, they instantly redistribute the planet's mass. The 2011 earthquake in Japan moved so much material that it shortened our days by 1.8 microseconds. The Earth literally shook itself into spinning faster. These discoveries emerged only recently because measuring such tiny changes requires incredible precision. We needed atomic clocks that could detect differences smaller than the blink of an eye. Without this technology, Earth's rotational secrets would have remained hidden forever. Understanding these changes matters more than you might think. Every GPS satellite, every computer network timestamp, and every international communication relies on precise timekeeping. When Earth's rotation changes, our entire technological infrastructure must adapt. The beautiful truth is that Earth's variable rotation reveals our planet's living nature. We inhabit a world that constantly responds to changes, adjusting its fundamental properties to maintain balance. This isn't chaos. It's the elegant dance of a planet that's perfectly tuned to support life. Imagine if your watch gained or lost a few seconds every day, and you had to constantly reset it to match the correct time. That's exactly what happens with Earth's rotation and our atomic clocks. When these two timekeeping systems disagree, something called a leap second must fix the mismatch. The conflict began in 1972 when atomic clocks became the official measure of time. These incredibly precise instruments tick based on atomic vibrations, never varying. But Earth's rotation follows its own rules, speeding up or slowing down as conditions change. The two timing systems slowly drift apart. Here's where it gets interesting. When the difference reaches 0.9 seconds, international timekeepers add or subtract a leap second to bring atomic time back in line with Earth time. It sounds simple, but this 1 second adjustment creates chaos in our interconnected world. Computer systems hate leap seconds. They're programmed to expect time to flow smoothly forward, never jumping or repeating. When a leap second appears, some systems crash, websites fail, and financial markets can experience disruptions. The tiny adjustment that fixes Earth's timing nearly breaks human technology. Your smartphone handles this automatically. It receives updated time signals that include leap second information, adjusting seamlessly without you ever knowing. But behind the scenes, engineers work frantically to ensure critical systems survive these temporal hiccups. The most recent leap second occurred on New Year's Eve 2016. At 11:59 p.m., instead of rolling over to midnight, clocks displayed 11:59:60 p.m. for 1 second. Then midnight arrived. This extra second helped atomic time catch up with Earth's slightly slower rotation. But here's the surprising part. Earth's recent speed-up might eliminate the need for future leap seconds. Since 2020, our planet has been spinning faster than atomic time, If this continues, we might need to subtract a second instead of adding one. It would be the first negative leap second in history. The debate over leap seconds has split the scientific community. Some argue they're essential for keeping human time connected to Earth's natural rhythms. Others claim they cause more problems than they solve, advocating for their elimination entirely. Astronomers need leap seconds to keep their telescopes pointed accurately. When they track stars across the sky, they rely on Earth's rotation as their reference. Without leap seconds, astronomical observations would gradually drift out of alignment with stellar positions. Navigation systems face the opposite problem. GPS satellites broadcast atomic time, which doesn't include leap seconds. When leap seconds occur, the difference between GPS time and civilian time grows by 1 second. Special software must handle this conversion to prevent navigation errors. The International Earth Rotation and Reference Systems Service decides when to implement leap seconds. This small group of scientists monitors Earth's rotation continuously, comparing it to atomic time. When the difference approaches 0.9 seconds, they announce a leap second 6 months in advance. 27 leap seconds have been added since 1972. All were positive, adding an extra second to help atomic clocks catch up with Earth's gradually slowing rotation. But Earth's recent acceleration might soon require the first negative leap second, removing a second instead. This seemingly tiny adjustment reveals the delicate balance between natural and artificial timekeeping. We've created clocks so precise they expose the imperfections in our planet's rotation. Now we must constantly adjust between these two versions of time, maintaining the illusion that days are always exactly 24 hours long. The mystery of Earth's changing rotation began with a lighthouse keeper named Samuel Johnson in 1889. Every night, he watched stars cross the sky, using their positions to verify his clock's accuracy. But something seemed wrong. The stars were arriving a few seconds early. Johnson documented these discrepancies meticulously, not knowing he was witnessing one of astronomy's greatest discoveries. His lighthouse logbooks would later help scientists realize that Earth's rotation wasn't constant. Our planet was a cosmic timepiece that sometimes ran fast or slow. The breakthrough came when astronomers compared Johnson's observations with similar records worldwide. Lighthouse keepers, ship navigators, and railway timekeepers all reported the same strange phenomenon. Star positions didn't match their carefully maintained clocks. Initially, scientists blamed the clocks. Mechanical timepieces were notoriously unreliable, gaining or losing minutes each day. But when multiple precision chronometers showed identical discrepancies, investigators realized something more profound was happening. Earth itself was the inaccurate timekeeper. The first scientific proof came in 1935 when Harold Spencer Jones analyzed decades of astronomical observations. He compared star positions recorded at different observatories, looking for patterns in the timing errors. What he found shocked the scientific community. Earth's rotation varied seasonally. During spring and summer, Earth spun slightly faster than average. Fall and winter brought slower rotation. The pattern repeated year after year with remarkable consistency. Spencer Jones had discovered that our planet's rotation responded to seasonal changes in atmosphere and ocean circulation. But measuring these tiny variations required incredible precision. Early astronomers used mechanical clocks that lost or gained several seconds daily. They needed a more stable reference than human-made timepieces. The solution came from the stars themselves. Quasars, those distant galactic powerhouses, became Earth's ultimate timekeepers. These objects lie billions of light years away, so far that they appear motionless against Earth's rotation. By tracking quasar positions with radio telescopes, scientists could measure our planet's spin with unprecedented accuracy. The technique, called very long baseline interferometry, combines signals from radio telescopes across the globe. When these telescopes observe the same quasar simultaneously, they create a virtual antenna thousands of miles wide. This system can detect changes in Earth's rotation smaller than a millisecond. World War II accelerated the research when military navigation demanded precise timekeeping. Radar systems needed synchronization across continents, pushing technology toward atomic precision. The war effort unknowingly created tools that would revolutionize our understanding of planetary rotation. The first atomic clock, built in 1949, changed everything. Instead of relying on mechanical pendulums or spring mechanisms, atomic clocks used the vibrations of cesium atoms. These natural oscillators provided a timekeeping reference more stable than Earth itself. By the 1960s, atomic clocks revealed the full extent of Earth's rotational variations. Scientists could track changes lasting minutes, hours, days, or years. They discovered that our planet responded to everything from earthquakes to seasonal weather patterns. The detective story continues today with a global network of monitoring stations. Atomic clocks, radio telescopes, and GPS satellites work together to track Earth's rotation in real time. Every day brings new measurements, adding details to our understanding of planetary dynamics. This investigation revealed something beautiful about scientific discovery. A lighthouse keeper's curiosity about early stars led to one of the most precise measurements in human history. Johnson's simple observations opened a window into the hidden mechanics of our rotating world. Step outside and feel the wind on your face. That breeze you're experiencing is actually changing how fast Earth spins. Every gust of wind, every ocean wave, and every raindrop contributes to our planet's rotation speed. Earth isn't a solid ball spinning in isolation. It's a dynamic system where every movement matters. Picture Earth as a washing machine with an unbalanced load. When clothes bunch up on one side, the machine wobbles and changes its rotation rhythm. Our planet does something similar, except instead of clothes, it's redistributing water, air, and ice. These movements constantly adjust Earth's spin. The atmosphere weighs about 5.5 quadrillion tons. When this massive envelope of air moves, it affects Earth's rotation through conservation of angular momentum. During strong westerly winds, the atmosphere spins faster than Earth's surface. To compensate, the solid planet below spins slightly slower. Ocean currents carry even more dramatic effects. The Gulf Stream alone transports 30 times more water than all the world's rivers combined. When this massive current shifts its path or intensity, Earth's rotation responds immediately. El Niño events, which redirect ocean currents across the Pacific, can change day length by several milliseconds. Seasonal changes create the most predictable rotational variations. Each winter, massive amounts of water freeze into ice and snow, locking liquid into solid form, mostly in the northern hemisphere. This redistribution moves mass toward Earth's rotation axis, speeding up the planet like a figure skater pulling in her arms. Spring reverses this effect dramatically. Melting snow and ice flow toward the oceans, moving mass away from the poles. Earth slows down as the released water spreads across lower latitudes. The annual cycle of freezing and melting creates a rotational heartbeat that repeats every year. But climate change is disrupting these patterns. Glaciers that once accumulated ice during winter now melt year-round. The Greenland ice sheet loses about 280 billion tons of ice annually. This massive transfer of water from land to ocean affects Earth's rotation permanently, not just seasonally. Groundwater extraction adds another layer of complexity. Humans pump trillions of gallons of water from underground aquifers every year. Most of this water eventually reaches the oceans, contributing to sea level rise and rotational changes. We're literally moving enough water to affect planetary spin. Major storms demonstrate Earth's sensitivity to mass redistribution. Hurricane Katrina's storm surge moved so much water that scientists detected a tiny change in Earth's rotation. The water displacement lasted only hours, but sensitive instruments caught the rotational hiccup. Forest fires contribute their own effects. When vast areas burn, they release water vapor and carbon dioxide into the atmosphere. This redistribution of mass, from solid vegetation to atmospheric gases, subtly influences Earth's spin. The Australian bushfires of 2019 to 2020 were so extensive, they likely affected global rotation. Even human activities leave rotational fingerprints. The Three Gorges Dam in China holds 42 billion tons of water behind its walls. When this reservoir filled, it moved enough mass to slow Earth's rotation by 0.06 microseconds. The dam literally changed the length of every day. Urban development plays a smaller but measurable role. As cities grow and concentrate mass in specific locations, they create tiny rotational effects. The concrete, steel, and accumulated materials of major metropolitan areas represent significant mass redistributions on a planetary scale. This constant motion reveals Earth as a living, breathing system. Every weather pattern, every seasonal change, and every geological process contributes to a planetary symphony of rotation. We live on a world that never stops adjusting, never stops responding to the forces that shape it. Something unprecedented began happening to Earth in 2020. For decades, our planet had been gradually slowing down, following the predictable pattern of tidal friction. Then suddenly, Earth decided to speed up. The change was so dramatic that 2020 recorded the shortest days in human history. The numbers tell an extraordinary story. On July 19th, 2020, Earth completed a rotation 1.47 milliseconds faster than the standard 24-hour day. This might seem insignificant, but it shattered records. Previous speed variations rarely exceeded 1 millisecond. Earth was clearly responding to something new. By the end of 2020, our planet had set 28 records for the shortest days ever measured. The trend continued into 2021, with Earth maintaining its accelerated pace. Scientists watched in fascination as their carefully calibrated predictions fell apart. The planet was writing its own rules. What made this acceleration so puzzling was its sudden onset. Earth's rotation typically changes gradually over months or years. But this speed-up appeared almost overnight and persisted for months. Something had fundamentally altered our planet's rotational dynamics. Climate scientists initially suspected melting ice. As glaciers and polar ice caps disappear, they redistribute massive amounts of water from the poles to the oceans. This should slow Earth's rotation, like a figure skater extending her arms. But the opposite was happening. Earth was spinning faster despite ongoing ice loss. Ocean current changes offered another explanation. The global conveyor belt of ocean circulation had been disrupting due to climate change. When currents shift their patterns or intensity, they affect Earth's rotation through conservation of angular momentum. But tracking these changes required more research. Atmospheric pressure variations became a leading suspect. The COVID-19 pandemic had reduced human industrial activity worldwide. Fewer flights meant different atmospheric circulation patterns. Reduced pollution allowed different heat absorption and air movement. These changes might have affected Earth's rotation. Some scientists pointed to deep Earth processes. Our planet's liquid iron core spins at its own rate, sometimes faster or slower than the solid surface above. Changes in core rotation can affect surface rotation through magnetic coupling. Perhaps something had shifted in Earth's interior dynamics. The jet stream provided another clue. This high-altitude river of air had been behaving erratically, creating unusual weather patterns worldwide. When jet streams shift position or intensity, they redistribute atmospheric mass, potentially affecting Earth's rotation through complex momentum exchanges. Seismic activity offered additional evidence. While major earthquakes can instantly change rotation, smaller seismic events might contribute cumulative effects. The period of Earth's acceleration coincided with increased volcanic activity in several regions, suggesting possible connections. Groundwater depletion emerged as a surprising factor. Humans extract about 1,000 cubic kilometers of groundwater annually. This water eventually reaches the oceans, contributing to sea level rise and mass redistribution. The accelerated pumping during droughts might have affected rotational patterns. Solar activity added another variable. The sun's magnetic field and radiation output influence Earth's upper atmosphere, causing it to expand or contract. These changes affect atmospheric mass distribution, and potentially Earth's rotation. Solar cycle variations might contribute to rotational anomalies. By 2022, Earth's acceleration began slowing. Days gradually returned toward their normal length, though they remained shorter than the long-term average. The mysterious speed-up seemed to be naturally correcting itself, leaving scientists with more questions than answers. Current measurements show Earth's rotation continuing to fluctuate unpredictably. Some days are faster, others slower, with no clear pattern emerging. Our planet appears to be in a transitional state, adjusting to forces that scientists are still trying to understand. This rotational mystery demonstrates how much we still don't know about our home planet. Despite decades of precise measurements and sophisticated models, Earth can still surprise us with behavior that challenges our understanding of planetary physics. Imagine holding a spinning figure skater by her hands, then suddenly letting go. She would pull her arms close to her body and spin faster. Earth does something remarkably similar when ice melts. As glaciers disappear and water flows from the poles toward the equator, our planet redistributes its mass and changes its rotation speed. The physics is elegantly simple. Ice locked in glaciers sits close to Earth's rotation axis, especially in Greenland and Antarctica. When this ice melts, the water flows into oceans spread across the globe. This moves mass away from the rotation axis, which should slow Earth's spin according to conservation of angular momentum. Greenland provides the most dramatic example of this ice-to-water transformation. The island's ice sheet contains enough frozen water to raise global sea levels by 24 feet if it melted completely. Currently, Greenland loses about 280 billion tons of ice each year. That's equivalent to 40 million African elephants' worth of water flowing into the oceans annually. But here's where the story gets complicated. While massive ice loss should slow Earth's rotation, recent measurements show the opposite happening. Earth has been spinning faster, not slower. This contradiction puzzled scientists until they realized ice loss is just one factor in a complex rotational equation. Antarctica adds another layer of complexity to the ice equation. While its ice sheets are also melting, Antarctica's ice loss pattern differs from Greenland's. Some regions gain ice, while others lose it rapidly. The net effect creates rotational influences that scientists are still trying to fully understand. Seasonal ice changes provide clearer examples of rotation effects. Every winter, massive amounts of water freeze into ice and snow across the northern hemisphere. This concentrates mass closer to Earth's rotation axis, speeding up the planet's spin by about 0.3 milliseconds. Spring melting reverses this effect, slowing rotation as water redistributes. Mountain glaciers contribute their own rotational signatures. The Swiss Alps, Rocky Mountains, and Himalayas all lose glacial ice that flows into rivers and eventually reaches the sea. While each glacier's contribution seems tiny, the combined effect of thousands of melting glaciers worldwide creates measurable rotational changes. Sea ice presents a different dynamic. Unlike land-based ice, floating sea ice doesn't change sea level when it melts, but it does affect ocean circulation patterns, which influence Earth's rotation through complex momentum exchanges. Arctic sea ice loss has been particularly dramatic, potentially contributing to rotational variations. The timing of ice loss matters crucially for rotational effects. Gradual melting over decades allows Earth's rotation to adjust slowly, but rapid melting events like the collapse of ice shelves can create sudden rotational changes that sensitive instruments detect immediately. Post-glacial rebound adds another twist to the ice story. In regions where massive ice sheets once pressed down the land, the ground is still rising as it recovers from the weight. This vertical movement of solid Earth affects mass distribution and contributes to rotational variations that persist thousands of years after the ice disappeared. Ice loss accelerates through feedback loops that amplify rotational effects. As ice melts, it exposes darker surfaces that absorb more heat, accelerating further melting. This process, called ice albedo feedback, means rotational changes from ice loss will likely accelerate in coming decades. Climate models predict dramatic increases in ice loss rates. The Greenland ice sheet, could lose ice 3 times faster by 2050 compared to current rates. Such massive water redistribution would create rotational effects larger than any measured in human history. Modern satellite missions track ice loss with unprecedented precision. The GRACE satellites measure gravitational changes caused by ice redistribution, providing real-time data on how melting affects Earth's rotation. These measurements reveal ice loss happening faster than most climate models predicted. The ice factor illustrates how climate change affects Earth in ways we're just beginning to understand. Every melting glacier, every disappearing ice sheet, every seasonal freeze and thaw cycle contributes to the complex dance of planetary rotation. Beneath the waves lies a hidden engine that influences how fast Earth spins. Ocean currents carry more water than all the world's rivers combined, creating massive flows that stretch across entire ocean basins. When these currents change speed or direction, they affect Earth's rotation through the fundamental physics of momentum conservation. The Gulf Stream demonstrates this principle perfectly. This oceanic superhighway carries warm water from the Caribbean toward Europe, at speeds reaching 5 miles per hour. The current transports about 30 times more water than the Amazon River, creating a flow so powerful it influences Earth's rotation measurably. Think of ocean currents as moving parts of a planetary machine. When currents flow eastward, they spin in the same direction as Earth's rotation. Through momentum conservation, this makes the solid Earth beneath spin slightly slower to compensate. Westward currents have the opposite effect, speeding up Earth's rotation. El Niño provides the most dramatic example of current-driven rotational changes. During El Niño events, trade winds weaken across the Pacific Ocean, allowing warm water to flow eastward towards South America. This massive redistribution of ocean mass changes Earth's rotation by several milliseconds, creating longer days. La Niña reverses this pattern. Stronger trade winds push warm surface water westward, concentrating it in the western Pacific. This redistribution moves mass away from the Americas and toward Asia, affecting Earth's rotation in the opposite direction from El Niño events. The Antarctic circumpolar current creates the most consistent rotational influence. This massive current circles Antarctica continuously, carrying more water than any other ocean current. Its steady flow provides a rotational baseline that scientists use to detect changes in other ocean systems. Seasonal current variations follow predictable patterns that show up in Earth's rotation data. Summer heating strengthens some currents while weakening others. Winter cooling reverses these effects. The annual cycle of current changes creates rotational variations that repeat each year with remarkable consistency. Deep ocean currents contribute their own rotational effects. These slow-moving flows carry cold, dense water along ocean floors, completing a global circulation pattern called the thermohaline circulation. Changes in this deep circulation can affect Earth's rotation over longer timescales than surface currents. Climate change is disrupting ocean current patterns worldwide. Melting ice adds fresh water to the oceans, changing water density and affecting current strength. Warming temperatures alter evaporation patterns, further modifying ocean circulation. These changes contribute to unpredictable rotational variations. The Kuroshio current off Japan provides another example of rotational influence. This western boundary current carries warm water northward at speeds comparable to the Gulf Stream. When typhoons or seasonal changes alter the Kuroshio's path, scientists can detect the rotational effects in precision timing measurements. Tidal currents add complexity to oceanic rotational effects. While tides themselves slow Earth's rotation through friction, tidal currents create additional momentum exchanges. The interaction between tidal forces and ocean basin geometry produces current patterns that influence rotation on daily and monthly cycles. Satellite altimetry reveals how ocean surface heights change as currents shift. When currents strengthen, they create slight elevation changes that redistribute mass across ocean surfaces. These height variations, measured precisely from space, help scientists understand current-driven rotational effects. Computer models of ocean circulation now include rotational physics. These models simulate how changing currents affect Earth's spin, helping scientists predict rotational variations based on oceanic conditions. The models reveal complex feedback loops where rotational changes influence atmospheric patterns, which then affect ocean currents. The relationship between ocean currents and Earth's rotation demonstrates how interconnected our planet's systems are. Changes in one part of the ocean can affect rotation globally, showing that Earth truly operates as an integrated system where everything influences everything else. The air around you weighs more than you might imagine. Earth's entire atmosphere has a mass of 5.5 quadrillion tons, and when this enormous envelope of air moves, it affects how fast our planet spins. Every breeze, every storm, and every seasonal wind shift contributes to changes in Earth's rotation through the physics of angular momentum. Picture the atmosphere as a massive tire surrounding Earth. When winds blow from west to east, the atmospheric tire spins faster than Earth's surface. To maintain total angular momentum, the solid planet below must spin slightly slower to compensate. Eastward winds slow Earth's rotation, while westward winds speed it up. The jet stream creates the most significant atmospheric effects on rotation. This high-altitude river of air flows at speeds up to 200 miles per hour, carrying enormous amounts of atmospheric mass. When jet streams strengthen or change position, they create measurable changes in Earth's rotation within days. Seasonal wind patterns produce the most predictable rotational variations. During Northern Hemisphere winter, cold air becomes denser and sinks closer to Earth's surface. This concentrates atmospheric mass nearer to the rotation axis, speeding up Earth's spin like a figure skater pulling in her arms. The effect adds about 0.3 milliseconds to rotation speed. Summer reverses this seasonal pattern. Warm air expands and rises higher into the atmosphere, moving mass away from Earth's rotation axis. This atmospheric expansion slows the planet's rotation, creating longer days during warm months. The annual cycle of heating and cooling drives predictable rotational changes. Trade winds demonstrate how persistent atmospheric patterns affect rotation. These steady eastward flows near the equator carry atmospheric momentum continuously. When trade winds strengthen during certain climate cycles, they slow Earth's rotation measurably. Weakening trade winds have the opposite effect. Monsoon systems create dramatic seasonal rotational effects. During monsoon season, massive air movements redistribute atmospheric mass across continents. The Indian monsoon alone moves enough air to affect Earth's rotation by fractions of milliseconds, demonstrating how regional weather patterns have global effects. Hurricane seasons contribute their own rotational signatures. These massive storm systems carry enormous atmospheric energy, creating temporary rotational effects as they develop and dissipate. While individual storms have tiny effects, active hurricane seasons with multiple major storms can influence Earth's rotation measurably. El Niño and La Niña events alter global wind patterns so dramatically they affect Earth's rotation for months or years. During El Niño, weakened trade winds reduce the atmospheric contribution to rotational slowing. La Niña strengthens trade winds, enhancing their rotational effects. The stratosphere, though thin, influences rotation through its own wind patterns. Stratospheric winds blow in opposite directions seasonally, creating the phenomenon known as the quasi-biennial oscillation. These high-altitude wind changes contribute to rotational variations on timescales of 2 to 3 years. Mountain ranges affect atmospheric rotational contributions by disrupting wind patterns. The Rocky Mountains, Himalayas, and Andes all create standing wave patterns in atmospheric flow. These disruptions redistribute atmospheric momentum, contributing to regional variations in rotational effects. Climate change is altering atmospheric contributions to Earth's rotation. Changing temperature patterns affect wind strength and direction globally. The jet stream has become more erratic, creating unpredictable rotational variations. Arctic warming weakens temperature gradients that drive atmospheric circulation. Atmospheric pressure variations create additional rotational effects. High-pressure systems concentrate more air mass in specific regions, while low-pressure systems spread mass over larger areas. The daily movement of pressure systems creates small but detectable rotational variations. Computer models now simulate atmospheric effects on rotation with increasing accuracy. These models combine weather prediction with rotational physics, helping scientists understand how changing atmospheric patterns influence Earth's spin. The models reveal complex interactions between different atmospheric layers. The atmosphere's influence on Earth's rotation shows how dynamic our planet really is. Every time wind patterns change, they affect the speed of rotation. We live on a world where the air itself participates in the dance of planetary motion. On March 11, 2011, the ground beneath Japan shifted violently. The magnitude 9.0 earthquake that struck off the coast moved so much rock and sediment that it literally changed how fast Earth spins. In an instant, the planet's rotation sped up, making every day 1.8 microseconds shorter. The earthquake had shaken time itself. The physics behind this phenomenon follows the same principle as a figure skater's spin. When the skater pulls mass closer to her body, she spins faster. During the Japan earthquake, massive amounts of rock moved toward Earth's rotation axis, concentrating mass and increasing rotational speed. The earthquake shifted the main island of Honshu 8 feet eastward and moved it 2 feet closer to Earth's center. This redistribution of solid rock mass affected the entire planet's rotation instantly. Seismic waves from the quake traveled through Earth's interior, but the rotational change was permanent. Scientists calculated that the earthquake moved enough mass to alter Earth's rotation using computer models of the fault displacement. The rupture zone stretched over 300 miles long and 150 miles wide, displacing an estimated 10 billion tons of rock. This massive redistribution created the rotational speedup. The 2004 Indian Ocean earthquake that caused the devastating tsunami also affected Earth's rotation. This magnitude 9.1 quake shortened days by 6.8 microseconds, even more than the Japan earthquake. The longer fault rupture and greater mass displacement created a larger rotational effect. But not all earthquakes speed up Earth's rotation. The direction and depth of fault movement determine the rotational outcome. Earthquakes that move mass away from Earth's rotation axis can slow the planet's spin instead. The 1960 Chilean earthquake, the strongest ever recorded, actually made days longer. Smaller earthquakes contribute cumulative rotational effects that scientists are just beginning to understand. While individual moderate quakes don't produce measurable changes, the combined effect of thousands of smaller earthquakes worldwide might influence Earth's rotation over longer timescales. The aftermath of major earthquakes continues affecting rotation through aftershocks and crustal adjustments. The Japan earthquake triggered thousands of aftershocks over months, each one contributing tiny additional changes to Earth's rotation. The cumulative effect prolonged the rotational impact. Volcanic eruptions create similar but different rotational effects. When volcanoes eject massive amounts of material into the atmosphere, they redistribute mass from solid Earth to the air above. This can temporarily affect rotation until the volcanic material settles back to the surface. Underground nuclear tests during the Cold War era contributed their own rotational signatures. These powerful explosions moved rock and created underground cavities, slightly redistributing Earth's mass. While individual tests had tiny effects, the combined impact of hundreds of nuclear explosions was measurable. Mining operations provide ongoing examples of human-caused rotational effects. Large open-pit mines move billions of tons of material from underground to the surface. Coal mining, copper extraction, and other industrial activities redistribute mass on scales large enough to affect Earth's rotation minutely. The Three Gorges Dam in China created one of the largest human-made rotational changes. When the reservoir filled with 42 billion tons of water, it moved mass away from Earth's rotation axis, slowing the planet's spin by 0.06 microseconds. The dam literally changed the length of every day. Glacial isostatic adjustment contributes ongoing rotational changes as landmasses continue rising or sinking in response to ancient ice sheets. Regions like Scandinavia and northern Canada are still rebounding from Ice Age glaciation, creating slow but persistent rotational effects. Modern earthquake monitoring systems can predict rotational changes before they're measured. When seismic networks detect major earthquakes, computers calculate expected rotational effects based on fault geometry and displacement magnitude. These predictions usually match subsequent precision measurements. The relationship between earthquakes and Earth's rotation reveals how dynamic our planet really is. Every fault movement, every volcanic eruption, and every mass redistribution contributes to the complex dance of planetary rotation. We live on a world where geological events literally shake the foundations of time itself. Every night, the moon rises over Earth, pulling at our oceans and creating the tides. But this celestial dance does something far more profound than moving water up and down beaches. The moon is gradually slowing Earth's rotation, stealing energy from our planet's spin and using it to spiral slowly away from us. The process works through tidal friction, one of the most elegant examples of physics in action. As the moon's gravity pulls on Earth's oceans, it creates two bulges of water, one facing the moon and one on the opposite side. Earth rotates faster than the moon orbits, so these tidal bulges stay slightly ahead of the moon's position. This offset is crucial. The moon's gravity pulls backward on the leading tidal bulge, acting like a gentle brake on Earth's rotation. Meanwhile, Earth's gravity pulls the moon forward through the same interaction, adding energy to the moon's orbit and causing it to drift gradually away from us. The numbers tell an extraordinary story. Earth's rotation is slowing by about 2.3 milliseconds per century due to tidal friction. This might seem insignificant, but it adds up over geological time. When dinosaurs ruled the Earth 100 million years ago, days were only about 21 hours long. Ancient coral fossils provide evidence of this rotational slowing. Corals grow in daily and annual cycles that create permanent records in their calcium carbonate skeletons. Paleontologists can count these growth bands to determine how many days occurred in ancient years, revealing shorter days in the distant past. The moon is moving away from Earth at 3.8 centimeters per year, about the same rate that your fingernails grow. This gradual separation is powered entirely by energy stolen from Earth's rotation. As our days get longer, the moon's orbit grows larger in a perfectly balanced exchange. Tidal friction affects more than just day length. It's gradually synchronizing Earth and the moon into what scientists call tidal locking. Eventually, billions of years in the future, the same side of Earth will always face the moon, just as the same side of the moon now always faces Earth. Other celestial bodies contribute smaller tidal effects. The Sun creates its own tidal bulges in Earth's oceans, but because the Sun is much farther away than the Moon, solar tides are about half as strong as lunar tides. Venus, Jupiter, and other planets create barely detectable tidal effects. The solid Earth itself experiences tidal deformation. The Moon's gravity stretches and compresses Earth's rocky interior, creating solid tides that can move the ground up and down by several inches. This solid body tidal friction also contributes to rotational slowing, though much less than ocean tides. Tidal heating from this friction generates energy within both Earth and the Moon. On Earth, this heating is tiny compared to other energy sources. But for the Moon, tidal heating from Earth may have kept the lunar interior partially molten long after it should have cooled completely. The tidal relationship between Earth and Moon is gradually weakening as the Moon moves away. In the distant past, when the Moon was closer, tides were much stronger and rotational slowing was faster. Early Earth may have had days only 6 to 8 hours long when the Moon first formed. Ancient tidal records preserved in sedimentary rocks confirm this changing relationship. Rhythmite deposits show alternating layers created by tidal cycles millions of years ago. These geological clocks reveal that the Moon-Earth tidal system has been operating consistently throughout Earth's history. The eventual fate of the Earth-Moon system involves complete tidal locking. In about 50 billion years, if the Sun doesn't intervene first, Earth days and lunar months will both equal about 47 current days. The Moon will hang motionless in the sky, ending the tidal dance that has shaped our planet. This tidal relationship demonstrates how celestial mechanics operates on multiple timescales simultaneously. While we notice daily tides, the underlying process operates over millions of years, gradually reshaping the Earth-Moon system through the gentle but persistent force of gravitational interaction. Beneath your feet lies a hidden world that affects how fast Earth spins. Deep inside our planet, a molten iron core spins at its own rate, sometimes faster or slower than the solid Earth above. This inner dance between liquid metal and solid rock creates some of the most mysterious changes in Earth's rotation. Picture Earth as two nested spinning spheres. The outer sphere, made of solid rock, is the world we live on. Inside, it spins a liquid iron sphere nearly as large as Mars. These two spheres can rotate at slightly different rates, connected only through magnetic forces, and the thin layer where liquid meets solid. The liquid outer core, composed mainly of iron and nickel, generates Earth's magnetic field through its motion. As this molten metal swirls and convects, it creates electrical currents that produce the magnetism protecting us from cosmic radiation. But this same motion affects Earth's rotation in ways scientists are still discovering. When the liquid core spins faster than the solid Earth above, it transfers rotational energy upward through electromagnetic coupling. This can speed up the solid Earth's rotation measurably. When the core slows down, it has the opposite effect, acting like a brake on Earth's surface rotation. These core-mantle interactions happen on timescales of years to decades. Unlike atmospheric or oceanic changes that affect rotation monthly or seasonally, core dynamics create longer-term variations that persist for many years. Scientists call these changes decade variations in Earth's rotation. The inner core adds another layer of complexity to this deep Earth dance. This solid iron sphere at Earth's center rotates at its own rate, which may differ from both the liquid outer core and the solid surface above. Recent studies suggest the inner core sometimes rotates faster than Earth's surface, sometimes slower. Magnetic field measurements provide clues about core dynamics. When Earth's magnetic field changes strength or direction, it often correlates with rotational variations. This suggests that the same core processes affecting the magnetic field also influence Earth's rotation through electromagnetic coupling between layers. Computer simulations of core dynamics reveal incredibly complex flows within the liquid iron. Hot metal rises from the core mantle boundary, while cooler metal sinks, creating convection patterns that constantly evolve. These flows generate the magnetic field and drive changes in core rotation rate. The core's influence on Earth's rotation became apparent when scientists noticed that rotational changes often preceded magnetic field changes by several years. This suggested that core dynamics first affect rotation, then later influence the magnetic field through the same underlying processes. Seismic waves traveling through Earth's core provide another window into deep dynamics. These waves reveal that the inner core rotates slightly faster than Earth's surface, completing one extra rotation every 400 to 1,000 years. This differential rotation affects the electromagnetic coupling between core layers. The core mantle boundary, located 1,800 miles below the surface, plays a crucial role in rotational coupling. Irregularities on this boundary create topographic features that affect how the liquid core flows against the solid mantle above. These interactions transfer rotational momentum between core and surface. Temperature variations in the core create density differences that drive convection and affect rotation. Hotspots at the core mantle boundary may correlate with surface features like volcanic hotspots, suggesting connections between deep Earth processes and surface geology. Recent research suggests that changes in Earth's rotation might affect core dynamics in return, creating feedback loops between surface and interior processes. This would make Earth's rotation system even more complex, with the core both responding to and influencing surface rotational changes. The discovery that Earth's deep interior affects surface rotation reveals our planet as a far more dynamic system than previously imagined. We live on the surface of a world whose rotation is influenced by processes occurring thousands of miles below our feet, in a realm of liquid metal and extreme temperatures. In a laboratory in Boulder, Colorado, sits a clock that redefines the meaning of precision. This atomic timekeeper measures the vibrations of cesium atoms, ticking 9,192,631,770 times per second with unwavering accuracy. It won't lose or gain a second for 300 million years. This technological marvel makes it possible to detect when Earth's rotation changes by mere milliseconds. Atomic clocks revolutionize timekeeping by abandoning mechanical parts entirely. Instead of pendulums or springs, these devices use the natural vibrations of atoms as their timekeeping reference. Cesium atoms oscillate at exactly the same frequency everywhere in the universe, providing a truly universal standard for measuring time. The physics behind atomic clocks borders on the magical. When cesium atoms absorb energy, their electrons jump to higher energy levels. When the electrons fall back down, they release that energy as electromagnetic radiation at a precise frequency. This natural atomic oscillation becomes the tick of the ultimate timepiece. Before atomic clocks, the most accurate timepieces were mechanical chronometers that gained or lost several seconds per day. These errors made it impossible to detect Earth's tiny rotational variations. Scientists needed a timing reference more stable than the planet itself to reveal Earth's changing spin. The first atomic clock, built in 1949, changed everything. Suddenly, scientists possessed a timekeeper accurate enough to detect variations in Earth's rotation measured in milliseconds. For the first time, researchers could study how our planet's spin responds to changing conditions. Modern atomic clocks have achieved accuracy that defies imagination. The latest optical atomic clocks can detect time differences of less than 1 second in 15 billion years. That's more accurate than measuring the distance from Earth to the Sun within the width of a human hair. A global network of atomic clocks now monitors Earth's rotation continuously. These timepieces, located at observatories worldwide, compare their perfectly regular ticking with Earth's slightly irregular rotation. When the two timing systems disagree, it reveals how our planet's spin has changed. GPS satellites carry atomic clocks that must account for rotational variations. These space-based timepieces experience different gravitational fields than Earth-based clocks, creating relativistic effects that complicate timekeeping. Engineers must constantly adjust for both Earth's changing rotation and Einstein's theories of relativity. The precision of atomic clocks revealed phenomena nobody expected. Scientists discovered that Earth's rotation varies not just seasonally, but daily, hourly, and even minute by minute. Without atomic timing precision, these tiny variations would remain hidden forever. International timekeeping centers use atomic clocks to maintain coordinated universal time, the global standard that synchronizes computer networks, financial markets, and communication systems. This standard must constantly incorporate Earth's rotational variations to maintain accuracy. Optical atomic clocks represent the next generation of timekeeping precision. These devices use visible light frequencies instead of microwave radiation, achieving accuracy improvements of 100 times over traditional cesium clocks. They can detect gravitational effects that change time dilation by mere inches of altitude. The ticking of atomic clocks provides the steady heartbeat against which Earth's irregular rotation is measured. Every millisecond variation in day length shows up immediately in the comparison between atomic time and Earth time, revealing our planet's dynamic nature. Quantum mechanics makes atomic clock precision possible. The same physics that governs atomic behavior ensures that cesium atoms vibrate at identical frequencies regardless of temperature, pressure, or magnetic fields. This quantum consistency creates the ultimate natural metronome. Future atomic clocks may become even more precise, potentially detecting rotational variations smaller than those currently measurable. These ultra-precise timepieces might reveal new aspects of Earth's behavior that remain hidden at current measurement limits. The marriage of atomic physics and rotational astronomy demonstrates how seemingly unrelated scientific fields can combine to reveal profound truths about our world. Without the precision of atomic clocks, Earth's rotational secrets would remain forever locked away from human understanding. High above your head, a constellation of satellites maintains a constant vigil, monitoring Earth's every movement with precision that would have seemed impossible just decades ago. These space-based sentinels can detect when our planet's rotation changes by fractions of milliseconds, revealing secrets about Earth's inner workings that no ground-based instrument could discover. The Global Positioning System provides one of the most sensitive tools for measuring Earth's rotation. GPS satellites broadcast timing signals that depend on knowing exactly where they are and when they're transmitting. When Earth's rotation changes, it affects the geometry between satellites and ground stations, creating detectable timing errors. Each GPS satellite carries multiple atomic clocks that maintain incredibly precise time. Ground stations around the world receive these signals and compare arrival times to detect any variations. When Earth spins faster or slower than expected, it shows up immediately in the GPS timing data as systematic errors across the entire network. The GRACE satellites, launched in 2002, revolutionized the measurement of mass redistribution on Earth. These twin spacecraft follow each other in orbit, constantly measuring the distance between them using microwave signals. When mass moves on Earth's surface, it changes the gravitational field, which affects the satellite's orbits and the distance between them. GRACE. Data reveals how melting glaciers, changing ocean currents, and shifting groundwater affect Earth's rotation. As ice melts in Greenland, the satellites detect the gravitational changes caused by water redistributing from land to sea. This mass movement directly correlates with changes in Earth's rotational speed. Laser-ranging satellites provide another tool for rotation measurements. Ground stations aim powerful laser beams at satellites covered with reflective prisms. By measuring the time it takes light to travel to the satellite and back, scientists can determine satellite positions with millimeter accuracy. These laser measurements reveal how Earth's rotation axis wobbles as the planet's mass distribution changes. The rotation axis doesn't stay fixed in space, but moves in small circles due to seasonal mass redistributions and other effects. Satellite laser ranging tracks this polar motion with extraordinary precision. Very long baseline interferometry uses radio telescopes and satellite communications to measure Earth's rotation relative to distant quasars. This technique combines ground-based radio telescopes with satellite coordination to create a global measurement network that can detect rotational changes smaller than a millisecond. Satellite altimetry measures ocean surface heights with centimeter precision, revealing how ocean currents change and affect Earth's rotation. When ocean currents strengthen or weaken, they redistribute water mass and influence rotational speed. Satellites can track these changes in real time across all the world's oceans. The International Space Station contributes rotation measurements through its precise orbit tracking. As ISS orbits Earth every 90 minutes, ground stations monitor its position continuously. Changes in Earth's rotation show up as small but measurable variations in the station's orbital parameters. Weather satellites provide atmospheric data that helps explain rotational changes. These spacecraft monitor wind patterns, pressure systems, and temperature distributions that affect Earth's rotation through atmospheric momentum exchange. Combining space-based weather data with rotation measurements reveals cause and effect relationships. Satellite gravity measurements from multiple missions create a comprehensive picture of mass movement on Earth. The GRACE follow-on mission continues monitoring gravitational changes, while planned future missions will provide even more detailed measurements of how mass redistribution affects rotation. Communication satellites contribute to rotation monitoring through their need for precise pointing. These spacecraft must maintain exact orientations to keep their antennas aimed at Earth. When Earth's rotation changes, satellite operators must adjust pointing systems, creating another data source for rotation variations. The integration of multiple satellite systems creates a comprehensive Earth monitoring network. GPS provides timing precision, GRACE measures mass changes, laser ranging tracks, axis motion, and weather satellites monitor atmospheric effects. Together, these space-based tools reveal Earth's rotation in unprecedented detail. Future satellite missions will push measurement precision even further. Proposed gravity missions could detect mass changes equivalent to a few inches of water over areas the size of cities. These measurements will reveal new aspects of how Earth's rotation responds to environmental changes. At 11:59 p.m. on New Year's Eve 2016, something extraordinary happened. Instead of jumping to midnight, clocks around the world displayed 11:59:60 p.m. for exactly 1 second. This extra moment, called a leap second, was added to keep human timekeeping aligned with Earth's rotation. But that single second nearly broke the internet. The problem stems from a fundamental conflict between two types of time. Atomic clocks tick with mechanical precision, never varying their rate. But Earth's rotation follows natural rhythms, sometimes faster, sometimes slower. When these two timing systems drift apart by more than 0.9 seconds, a leap second bridges the gap. Computer systems hate leap seconds because they're programmed to expect time to flow smoothly forward. When a leap second appears, some servers crash, websites fail, and financial networks experience disruptions. The tiny adjustment that helps astronomical timekeeping creates chaos in our digital world. Reddit, LinkedIn, and dozens of other major websites crashed during the 2012 leap second. Airlines experienced reservation system failures. The Australian Stock Exchange suffered trading disruptions. A 1-second time adjustment caused millions of dollars in technical problems worldwide. Your smartphone handles leap seconds automatically through careful programming and network updates. Before each leap second, telecommunications companies push updates to cellular networks that include the timing adjustment. Most users never notice the extra second being added or subtracted, but behind the scenes, engineers work frantically to ensure critical systems survive leap seconds. Power grids, air traffic control systems, and financial trading networks all require special programming to handle these temporal anomalies. The preparation for each leap second takes months of planning. The scientific community is divided on whether leap seconds should continue. Astronomers argue they're essential for keeping human timekeeping connected to Earth's natural rotation. Without leap seconds, noon would gradually shift away from the sun's highest position in the sky. Technology companies lobby for abandoning leap seconds entirely. They argue the costs and risks of implementing these time adjustments outweigh their benefits. Google has developed a leap smear system that spreads the 1-second adjustment across an entire day to avoid sudden time jumps. The International Telecommunication Union has been debating the future of leap seconds for over a decade. Representatives from different countries and industries argue about whether to maintain, modify, or eliminate this unique timekeeping practice. The debate reflects deeper questions about humanity's relationship with natural time. GPS satellites broadcast atomic time without leap seconds, creating a growing discrepancy with civilian timekeeping. This GPS time now runs 18 seconds ahead of coordinated universal time, due to accumulated leap seconds since 1980. Special software must convert between these different time standards. Financial markets face particular challenges with leap seconds. Trading systems that process thousands of transactions per second cannot afford timing ambiguities. Some exchanges shut down during leap seconds to avoid potential problems, while others implement complex workarounds. The 27 leap seconds added since 1972 were all positive, extending the day by 1 second. But Earth's recent acceleration might soon require the first negative leap second, removing a second instead of adding one. Computer systems designed only for positive leap seconds might not handle this reversal correctly. Satellite navigation systems would benefit from eliminating leap seconds. Precise positioning requires knowing exactly what time it is, and the discontinuities created by leap seconds introduce potential errors. Military and civilian navigation systems must carefully handle these timing adjustments. The debate over leap seconds reflects broader tensions between natural and artificial timekeeping. Atomic clocks provide the stability that modern technology requires, but Earth's rotation connects us to the astronomical cycles that shaped human civilization for millennia. Some proposed solutions involve accumulating larger time differences before making adjustments. Instead of adding leap seconds when the difference reaches 0.9 seconds, adjustments might wait until several seconds of difference accumulate. This would reduce the frequency of disruptive time changes. The International Earth Rotation and Reference System Service decides when to implement leap seconds based on measurements of Earth's rotation. This small group of scientists holds responsibility for a decision that affects computer systems worldwide, demonstrating how Earth science influences modern technology. Something unprecedented happened to Earth in 2020. After decades of gradually slowing rotation, our planet suddenly began spinning faster. The acceleration was so dramatic that 2020 recorded 28 of the shortest days in human history. Earth was rewriting the rules of planetary timekeeping. The numbers reveal the extraordinary nature of this change. On July 19th, 2020, Earth completed a rotation 1.47 milliseconds faster than the standard 24-hour day. Previous speed records rarely exceeded 1 millisecond. Earth had entered uncharted territory for rotational velocity. By 2021, the acceleration continued with remarkable persistence. Earth maintained its faster-than-normal rotation for over a year, creating the shortest average day length since precise measurements began. The planet seemed determined to maintain its new, faster pace. Scientists initially struggled to explain this sudden speed-up. Earth's rotation typically changes gradually in response to predictable forces like tidal friction and seasonal mass redistribution. But this acceleration appeared almost overnight and showed no signs of following traditional patterns. Climate change offered one potential explanation. As glaciers melt and redistribute water from land to sea, they should slow Earth's rotation according to conservation of angular momentum. But the opposite was happening. Earth was spinning faster despite massive ongoing ice loss. Atmospheric changes became a leading suspect for the rotational acceleration. The COVID-19 pandemic had reduced industrial activity worldwide, potentially altering atmospheric circulation patterns. Fewer flights meant different jet stream dynamics. Reduced pollution allowed different heat absorption and air movement patterns. Ocean current modifications provided another possible cause. Climate change has been disrupting global ocean circulation, potentially affecting how water mass distributes around the planet. Changes in current strength or direction could influence Earth's rotation through momentum conservation. Deep Earth processes offered additional explanations. The liquid iron core spins at its own rate and can transfer rotational energy to the solid Earth above through electromagnetic coupling. Perhaps changes in core dynamics were driving the surface acceleration. Seismic activity during 2020 and 2021 might have contributed to the rotational changes. While individual earthquakes create instant but small rotational adjustments, the cumulative effect of increased global seismic activity could influence Earth's spin over longer periods. The jet stream's increasingly erratic behavior correlated with the rotational changes. Climate change has made this high-altitude wind pattern more variable, creating unusual atmospheric mass distributions. These changes could affect Earth's rotation through atmospheric momentum exchange. Groundwater depletion emerged as an unexpected factor. Humans extract about 1,000 cubic kilometers of groundwater annually, eventually contributing to sea level rise. The accelerated pumping during recent droughts might have affected rotational patterns through mass redistribution. By late 2021, Earth's acceleration began moderating. Days gradually returned toward normal length, though they remain shorter than the long-term average. The mysterious speed-up seemed to be naturally correcting itself, leaving scientists with more questions than answers. Current measurements show Earth's rotation continuing to fluctuate unpredictably. Some days are faster, others slower, with no clear pattern emerging. The planet appears to be in a transitional state, adjusting to forces that scientists are still working to understand. The recent acceleration demonstrates how much remains unknown about our home planet. Despite decades of precise measurements and sophisticated models, Earth can still surprise us with behavior that challenges our understanding of planetary physics and climate dynamics. This rotational mystery highlights the interconnected nature of Earth's systems. Atmospheric changes, ocean dynamics, ice loss, and deep Earth processes all contribute to a complex dance that determines how fast our planet spins. We're witnessing planetary-scale physics in real time. The implications extend beyond scientific curiosity. If Earth's rotation becomes more unpredictable, it could affect GPS accuracy, communication networks, and any technology that depends on precise timekeeping. Understanding these changes becomes crucial for maintaining our technological infrastructure. A drought in California doesn't just affect local agriculture, it changes how fast Earth spins. When massive amounts of groundwater disappear from underground aquifers, the resulting mass redistribution influences our planet's rotation in ways that scientists are just beginning to understand. Regional changes create global effects in Earth's interconnected system. The Amazon rainforest demonstrates this principle perfectly. During dry seasons, billions of tons of water evaporate from the forest and flow elsewhere as atmospheric moisture. This massive movement of water from land to air affects Earth's rotation by redistributing mass away from the surface and into the atmosphere above. Urban development creates its own rotational fingerprints. As cities grow and concentrate mass in specific locations, they represent significant redistribution of materials on Earth's surface. The concrete, steel, and accumulated infrastructure of major metropolitan areas contribute measurably to local mass concentrations that affect global rotation. Major reservoir systems provide dramatic examples of regional effects influencing planetary rotation. When the Three Gorges Dam in China filled with 42 billion tons of water, it moved enough mass to slow Earth's rotation by 0.06 microseconds. This single construction project changed the length of every day globally. Agricultural irrigation systems contribute ongoing rotational effects through groundwater extraction and redistribution. The Central Valley in California, the Great Plains in North America, and similar agricultural regions worldwide pump enormous amounts of groundwater that eventually reaches the oceans through rivers and atmospheric circulation. Seasonal snow accumulation and melting create predictable regional contributions to Earth's rotational variations. The Himalayas, Rocky Mountains, and other major mountain ranges accumulate massive amounts of snow each winter, then release it as meltwater during spring and summer. This annual cycle affects global rotation patterns. Mining operations redistribute mass on scales large enough to influence Earth's rotation. Open-pit copper mines, coal extraction, and oil production move billions of tons of material from underground to the surface. While individual operations have tiny effects, the combined global impact of industrial mining affects planetary mass distribution. Forest fires contribute regional effects through biomass redistribution. When vast areas burn, they convert solid vegetation into atmospheric gases and particulates. The Australian bushfires of 2019 to 2020 were so extensive they likely contributed measurable effects to global atmospheric mass distribution. Regional sea level changes create rotational effects through water mass redistribution. Areas experiencing rapid sea level rise concentrate more water mass locally, while regions with falling sea levels lose water mass. These regional variations in ocean mass distribution influence Earth's overall rotational dynamics. Volcanic eruptions provide examples of sudden regional mass redistributions affecting global rotation. Major eruptions can inject billions of tons of material into the atmosphere while removing mass from specific surface locations. The 1991 Mount Pinatubo eruption temporarily affected global atmospheric mass distribution. Glacial isostatic adjustment creates ongoing regional effects from ancient ice sheets. Regions like Scandinavia and northern Canada continue rising as land rebounds from Ice Age glaciation, while areas that received glacial meltwater continue sinking. These vertical land movements redistribute mass and affect rotation. The Sahara Desert influences Earth's rotation through seasonal dust storms that redistribute atmospheric mass. When massive dust clouds blow across the Atlantic Ocean, they carry enough particulate matter to create measurable changes in atmospheric mass distribution between continents. Wetland systems contribute rotational effects through their seasonal water storage cycles. Major wetland complexes like the Pantanal in South America or the Okavango Delta in Africa store and release enormous amounts of water seasonally, creating regional mass redistributions that affect global rotation. Hydroelectric reservoirs worldwide represent concentrated examples of mass redistribution. These artificial lakes store water that would otherwise flow to the oceans, creating mass concentrations at specific locations. The combined effect of thousands of reservoirs globally influences Earth's rotational dynamics. The interaction between regional effects and global rotation demonstrates Earth's fundamental interconnectedness. No region operates in isolation. Local changes in mass distribution, whether from human activities or natural processes, contribute to planetary-scale rotational variations that affect the entire world. Understanding these regional contributions helps scientists predict rotational changes and develop better models of Earth's dynamic behavior. As human activities increasingly modify regional mass distributions through development, agriculture, and resource extraction, their cumulative effects on planetary rotation will likely become more significant. How do you measure something as subtle as Earth's changing rotation speed? The challenge requires detecting variations smaller than the blink of an eye in a planet spinning at over 1,000 miles per hour. The solution combines atomic clocks, radio telescopes, and distant galaxies in one of the most precise measurements ever attempted. Very long baseline. Interferometry represents humanity's most sophisticated approach to measuring Earth's rotation. This technique uses radio telescopes separated by thousands of miles to observe the same distant quasars simultaneously. By comparing the arrival times of radio signals, scientists can determine Earth's orientation in space with extraordinary precision. Quasars serve as perfect reference points because they're billions of light years away. At such immense distances, these galaxies appear motionless relative to Earth's rotation. They provide fixed landmarks against which scientists can measure our planet's changing spin and orientation. The measurement process requires split-second coordination between radio telescopes worldwide. When telescopes in different continents observe the same quasar at exactly the same time, tiny differences in signal arrival times reveal Earth's precise orientation and rotation rate at that moment. Atomic clocks provide the timing precision necessary for these measurements. Each radio telescope site maintains atomic clocks synchronized to billionths of a second. Without this timing accuracy, the technique would be impossible because the measurements depend on detecting time differences smaller than human reaction time. The calculations involved in processing this data challenge even supercomputers. Scientists must account for Earth's rotation, the wobbling of its axis, tidal effects from the Moon and Sun, and relativistic effects from Einstein's theories. The final result reveals rotational changes measured in fractions of milliseconds. Atmospheric effects complicate these precise measurements. Radio waves from quasars must pass through Earth's ionosphere and troposphere before reaching ground-based telescopes. Changes in atmospheric density and water vapor content can affect signal timing, requiring careful corrections to achieve ultimate precision. The International VLBI Service coordinates measurements from observatories worldwide. This organization schedules observations, distributes data, and combines results from different telescope networks to produce the most accurate possible measurements of Earth's rotation and axis position. Laser ranging satellites provide an independent check on VLBI measurements. Ground stations aim powerful laser pulses at satellites covered with reflective prisms, measuring the time for light to travel to the satellite and back. This technique achieves millimeter precision in determining satellite positions and Earth's rotation. GPS satellites contribute another layer of rotational measurement precision. The global positioning system requires knowing Earth's exact orientation to maintain accurate navigation. When Earth's rotation changes, it affects GPS timing and positioning, providing another data source for rotational variations. The combination of different measurement techniques creates redundancy that increases confidence in the results. When VLBI, satellite laser ranging, and GPS measurements all show the same rotational changes, scientists can be certain they're detecting real variations in Earth's spin. Modern measurement systems can detect rotational changes happening in real time. Advanced data processing allows scientists to monitor Earth's rotation continuously, revealing variations that occur over hours, days, or weeks. This real-time capability helps correlate rotational changes with their causes. The precision achieved in Earth rotation measurements exceeds anything possible in other fields of science. Scientists can now detect rotational variations equivalent to changes in day length, smaller than the time it takes light to travel across a small city. Future measurement systems promise even greater precision. Proposed space-based VLBI systems would eliminate atmospheric effects entirely, potentially detecting rotational variations too small to measure with current ground-based techniques. These measurements reveal Earth as a dynamic, ever-changing system where tiny variations in rotation speed reflect complex interactions between atmosphere, oceans, ice, and solid Earth. The precision required to detect these changes represents one of humanity's greatest technological achievements. The ability to measure Earth's rotation with such extraordinary precision opens new possibilities for understanding our planet's behavior. Scientists can now study how climate change, natural disasters, and human activities affect the fundamental properties of our rotating world. Your body has no idea that yesterday was 1.7 milliseconds shorter than the day before. Despite Earth's constantly changing rotation speed, your circadian rhythms continue their steady 24-hour cycle, completely unaware of the tiny variations that fascinate scientists. Life has evolved to be remarkably tolerant of these planetary timing changes. The human biological clock operates with impressive flexibility. Even if days varied by several minutes instead of milliseconds, your body would adapt gradually without noticeable effects. Our circadian rhythms can adjust to time changes much larger than any rotational variation Earth produces naturally. Plants demonstrate similar tolerance to timing variations. Photosynthesis, growth cycles, and seasonal flowering all follow internal clocks that are far less precise than atomic timekeeping. A few milliseconds here or there makes no difference to biological processes that typically vary by minutes or hours. Animal migration patterns show no sensitivity to Earth's rotational variations. Birds, whales, and other migrating species navigate using magnetic fields, star positions, and internal compasses that operate on timescales much larger than rotational changes. These biological navigation systems are naturally immune to timing variations. Sleep patterns in humans remain completely unaffected by Earth's changing rotation speed. Your body's sleep-wake cycle is controlled by hormones and neural circuits that respond to light exposure, temperature, and social cues. Millisecond changes in day length fall far below the threshold of biological sensitivity. The tides, which directly reflect Earth's rotation through gravitational interactions with the Moon, show such small variations that marine life remains unaffected. Tide pool organisms, coastal birds, and other creatures that depend on tidal timing continue their behaviors normally despite rotational changes. Seasonal biological rhythms follow patterns established over millions of years of evolution. These systems are designed to handle natural variations much larger than any rotational changes. The annual cycles of hibernation, reproduction, and migration operate with timing windows measured in days or weeks, not milliseconds. Agricultural cycles demonstrate remarkable stability despite Earth's variable rotation. Crop planting, growing seasons, and harvest timing all follow patterns based on temperature, daylight duration, and seasonal weather. These factors vary far more than rotational timing and represent the natural variation that farming systems are designed to handle. Weather patterns show no sensitivity to rotational variations at the scales currently observed. Atmospheric systems operate on timescales of hours to days, with natural variability that dwarfs any effects from changing rotation speed. Storm systems, precipitation cycles, and seasonal patterns continue unchanged. Human behavioral rhythms adapt easily to timing variations much larger than rotational changes. We routinely adjust to daylight saving time changes, international travel across time zones, and shift work schedules. These lifestyle adaptations involve timing changes thousands of times larger than Earth's rotational variations. The food chain demonstrates resilience to timing variations through its inherent flexibility. Predator-prey relationships, pollination cycles, and ecosystem interactions all operate with natural timing variability that greatly exceeds any rotational effects. Life has evolved to handle uncertainty and variation. Medical research shows no correlation between Earth's rotational variations and human health outcomes. Sleep disorders, circadian rhythm disruptions, and seasonal affective patterns all relate to factors like light exposure and temperature changes, not to planetary rotation timing. Even precision-dependent biological processes remain unaffected by rotational changes. Enzyme reactions, cellular division cycles, and DNA replication all operate with internal timing mechanisms that are far less precise than the atomic clocks used to detect rotational variations. The psychological impact of knowing about rotational variations is virtually non-existent. Unlike other timing changes that humans notice, such as daylight saving time or jet lag, Earth's rotational variations occur below the threshold of human perception and cause no stress or adjustment difficulties. This biological tolerance to rotational variations reveals something profound about life's resilience. Evolution has created organisms capable of thriving despite natural variations in their environment. The tiny timing changes that challenge our most precise instruments are completely insignificant to the biological world. The disconnect between measurement precision and biological relevance demonstrates how technological advancement can reveal phenomena that have no practical impact on daily life. We can now detect changes that are fascinating scientifically but completely irrelevant biologically. While your body remains blissfully unaware of Earth's changing rotation speed, the computer networks that run modern civilization must constantly adapt to these tiny timing variations. GPS satellites, financial trading systems, and internet infrastructure all depend on precision timing that makes millisecond variations in Earth's rotation a significant technical challenge. GPS satellites face the most direct impact from rotational changes. These spacecraft broadcast timing signals that help determine positions on Earth's surface. When Earth's rotation speed changes, it affects the geometric relationships between satellites and ground receivers, potentially introducing errors in location calculations. Each GPS satellite carries atomic clocks synchronized to precise time standards. But these space-based clocks must account for Earth's variable rotation to maintain accuracy. Ground control systems continuously update satellite timing to compensate for rotational variations, ensuring that your smartphone's map application remains accurate. Financial trading systems require timing precision that makes Earth's rotational variations matter. High-frequency trading operations execute thousands of transactions per second, with profits measured in microseconds. When rotational changes affect timing synchronization between trading centers, they can influence market operations. The Internet's backbone infrastructure depends on synchronized timing across continents. Data packets traveling through fiber optic cables must arrive at precise intervals to maintain communication quality. Network timing protocols must account for Earth's rotational variations to prevent degradation in Internet performance. Power grid synchronization presents another challenge affected by rotational timing. Electrical systems across vast regions must operate in perfect synchrony to prevent blackouts. The timing systems that coordinate power generation and distribution must compensate for Earth's changing rotation speed. Air traffic control systems rely on precise timing for safe aircraft navigation. Radar systems, communication networks, and navigation aids all require synchronization that accounts for Earth's rotational variations. Flight safety depends on maintaining timing accuracy, despite planetary rotation changes. Cellular phone networks use timing synchronization to coordinate signals between cell towers. When Earth's rotation changes, it can affect the precise timing required for seamless communication as you move between cell coverage areas. Network operators must continuously adjust their systems. Scientific instruments around the world require timing coordination that accounts for rotational variations. Radio telescopes, particle accelerators, and other precision instruments must synchronize their operations despite Earth's changing rotation speed to maintain measurement accuracy. Computer servers that handle online transactions must maintain accurate timestamps despite rotational changes. Banking systems, e-commerce platforms, and database operations all depend on precise timing that requires accounting for Earth's variable rotation speed. Satellite navigation systems beyond GPS face similar challenges. The European Galileo system, Russian GLONASS, and Chinese Beidou all must compensate for Earth's rotational variations to maintain accurate positioning services worldwide. Television and radio broadcasting systems use timing synchronization that must account for rotational changes. The precise coordination required for live broadcasts, emergency alert systems, and signal quality depends on maintaining accurate timing despite Earth's variable rotation. Data center operations require synchronized timing across multiple facilities. Cloud computing services, online storage systems, and distributed computing networks all depend on precise timing that must compensate for Earth's rotational variations to prevent data corruption or loss. The global financial system depends on timestamp accuracy that makes rotational variations significant. Stock exchanges, currency trading, and international banking all require timing precision that must account for Earth's changing rotation speed to maintain proper transaction sequencing. Automated systems in manufacturing and transportation rely on precise timing coordination. Industrial control systems, railway scheduling, and logistics networks all depend on synchronized timing that must compensate for Earth's rotational variations to maintain operational efficiency. Emergency response systems require timing accuracy that accounts for rotational changes. 911 call centers, first responder coordination, and disaster response networks all depend on precise timing that must remain accurate despite Earth's variable rotation speed. The challenge of maintaining technological precision despite Earth's rotational variations demonstrates how our modern world depends on timing accuracy that exceeds natural planetary stability. We've created systems more precise than the planet they operate on. Climate change isn't just warming our planet and raising sea levels. It's actually altering how fast Earth spins by redistributing massive amounts of water, ice, and atmospheric mass around the globe. The same forces reshaping our climate are subtly but measurably changing the fundamental physics of our rotating world. Melting glaciers provide the most obvious connection between climate change and Earth's rotation. As ice sheets in Greenland and Antarctica lose mass, billions of tons of water flow from the polar regions into the world's oceans. This redistribution moves mass away from Earth's rotation axis, which should slow the planet's spin according to conservation of angular momentum. The numbers are staggering. Greenland alone loses about 280 billion tons of ice annually due to climate change. Antarctica contributes additional hundreds of billions of tons. This massive transfer of water from land to sea represents one of the largest ongoing mass redistributions in Earth's history. But the relationship between ice loss and rotation is more complex than simple physics might suggest. Recent measurements show Earth spinning faster despite accelerating ice loss. This apparent contradiction reveals how multiple climate-related factors interact to influence rotation in unexpected ways. Sea level rise concentrates more water mass in the oceans while reducing ice mass on land. But the distribution of this rising water isn't uniform globally. Some regions experience faster sea level rise than others due to ocean currents, gravitational effects, and regional climate patterns. This uneven distribution affects rotation differently than uniform water redistribution would. Changing ocean currents represent another climate rotation connection. As global warming alters temperature patterns, it disrupts the massive circulation systems that move water around the world's oceans. When currents like the Gulf Stream or Antarctic Circumpolar Current change strength or direction, they affect Earth's rotation through momentum conservation. The jet stream's increasingly erratic behavior due to climate change influences Earth's rotation through atmospheric momentum exchange. As Arctic warming reduces temperature gradients that drive jet stream flow, these high-altitude winds become more variable, creating unpredictable atmospheric contributions to rotational changes. Atmospheric pressure patterns are shifting due to climate change, affecting how air mass distributes around the planet. Changes in the strength and position of high and low pressure systems alter atmospheric contributions to Earth's rotation speed through the complex physics of momentum conservation. Extreme weather events intensified by climate change create temporary rotational effects. Stronger hurricanes, more severe droughts, and intense flooding all redistribute mass in ways that influence Earth's rotation. While individual events have small effects, the increased frequency of extreme weather adds cumulative rotational impacts. Groundwater depletion accelerated by climate change contributes to rotational changes. As droughts become more severe and frequent, increased pumping of underground water for agriculture and urban use redistributes mass from subsurface aquifers to surface reservoirs and eventually to the oceans. Vegetation changes due to shifting climate zones affect rotational dynamics through biomass redistribution. As forests expand in some regions while shrinking in others, the changing distribution of plant mass creates small but measurable effects on Earth's rotation through altered mass distribution patterns. Permafrost melting releases water previously locked in frozen ground, contributing to mass redistribution effects. As Arctic regions warm, vast amounts of water flow from thawed permafrost into rivers and eventually to the oceans, affecting Earth's rotational balance. Future climate projections suggest accelerating rotational effects as warming continues. Computer models predict that ice loss will accelerate, ocean circulation will become more disrupted, and atmospheric patterns will become more chaotic. These changes will create increasingly complex influences on Earth's rotation. The feedback loops between climate change and rotation create additional complications. As Earth's rotation changes, it can affect atmospheric and oceanic circulation patterns, which in turn influence climate. This creates complex interactions that make predictions increasingly difficult. Understanding climate rotation connections helps scientists interpret both climate data and rotational measurements more accurately. Changes in Earth's rotation provide an additional tool for monitoring climate change effects, while climate models can help predict future rotational variations. The discovery that climate change affects Earth's rotation adds another dimension to our understanding of how human activities influence planetary-scale processes. We're not just changing the climate, we're altering the fundamental dynamics of our spinning world. Predicting how fast Earth will spin tomorrow sounds like it should be straightforward. After all, we can forecast weather patterns, predict eclipses centuries in advance, and calculate spacecraft trajectories to other planets with incredible accuracy. But Earth's rotation follows its own chaotic rules that make it one of the most difficult planetary phenomena to predict. The challenge lies in Earth's complex, interconnected systems. Unlike the predictable orbits of planets around the Sun, Earth's rotation responds to countless variables. Melting ice, changing ocean currents, shifting atmospheric patterns, earthquakes, and even human activities. Each factor influences rotation through different physics and on different timescales. Weather prediction provides a useful comparison for understanding rotational forecasting difficulties. Meteorologists can predict weather patterns reasonably well for about a week, with accuracy declining rapidly beyond that. Earth's rotation prediction faces similar challenges, complicated by even more variables and longer timescales. Seasonal variations offer the most predictable rotational changes. Scientists know that Northern Hemisphere winter will speed up Earth's rotation as cold air becomes denser and sinks closer to the surface. Spring melting will slow rotation as ice becomes water and redistributes mass. These annual cycles repeat reliably enough for accurate seasonal predictions. Ocean current changes present greater forecasting challenges. While scientists understand how El Niño and La Niña events affect Earth's rotation, predicting when these climate cycles will occur remains difficult. Ocean systems operate on timescales of months to years, making rotational predictions uncertain beyond seasonal cycles. Atmospheric pressure variations follow somewhat predictable patterns linked to seasonal changes and large-scale weather systems. But the atmosphere's inherent chaos limits prediction accuracy to weeks or months for rotational effects driven by air mass redistribution. Ice loss from climate change creates long-term rotational trends that scientists can project with reasonable confidence. As global warming continues, glacial melting will likely continue affecting Earth's rotation predictably. But the rate and location of ice loss depend on complex climate feedback loops. Deep Earth processes pose the greatest prediction challenges. Changes in the liquid iron core that affect Earth's rotation operate on timescales of years to decades, but scientists have limited ability to predict when or how these deep changes will occur. Earthquake prediction remains impossible, making earthquake-driven rotational changes unpredictable. Major earthquakes can instantly change Earth's rotation by measurable amounts, but seismologists cannot predict when or where large earthquakes will occur with useful accuracy. Mathematical chaos theory explains why rotational prediction becomes impossible beyond certain time limits. Small changes in any of the factors affecting Earth's rotation can amplify over time, creating large, unpredictable effects. This sensitivity to initial conditions makes long-term prediction fundamentally impossible. Computer models of Earth's rotation incorporate data from atmospheric, oceanic, and climate systems to make the best possible predictions. These models work well for seasonal variations, but become unreliable for longer-term forecasts due to the accumulation of uncertainties. Current prediction capabilities extend reliably only a few months into the future for detailed rotational variations. Scientists can predict general trends like the seasonal speed-up during Northern Hemisphere winter, but cannot forecast specific day-length changes beyond short time periods. Improved monitoring systems are enhancing prediction capabilities gradually. Better measurements of ice loss, ocean currents, and atmospheric conditions provide more accurate input data for prediction models. Satellite systems now monitor Earth's mass distribution changes in real time. Machine learning approaches offer new possibilities for rotational prediction. Artificial intelligence systems trained on decades of rotational data might identify patterns too complex for traditional analysis. These systems could potentially extend useful prediction ranges. The International Earth Rotation and Reference Systems Service provides the most authoritative rotational predictions for technical applications. This organization combines data from monitoring stations worldwide to forecast rotational changes for GPS, navigation, and astronomical applications. Prediction limitations have practical implications for systems requiring precise timing. GPS satellites, communication networks, and scientific instruments must incorporate uncertainty estimates when using rotational predictions for operational planning. The fundamental unpredictability of Earth's rotation over long time periods reflects the complex nature of our planet. We inhabit a world whose basic properties emerge from the interaction of countless dynamic systems, creating behavior that defies simple prediction despite our sophisticated understanding of the underlying physics. Step back from Earth's daily rotational variations and consider the vast sweep of geological time. Our planet's spin has been slowing steadily for billions of years, gradually lengthening days from the brief rotations of early Earth to the familiar 24-hour cycle we know today. Understanding this long-term evolution reveals Earth's rotation as part of a cosmic story still unfolding. When Earth first formed 4.5 billion years ago, it spun much faster than today. Early Earth likely completed a rotation in just 6 to 8 hours, creating days shorter than a modern work shift. The planet was a rapidly spinning ball of molten rock, rotating fast enough that its equatorial bulge was more pronounced than today. The Moon's formation dramatically altered Earth's rotational history. The giant impact that created our lunar companion knocked Earth's rotation axis into its current tilted position and began the long process of tidal slowing that continues today. Without this impact, Earth's rotation might have evolved very differently. Ancient coral fossils provide direct evidence of Earth's changing rotation over geological time. These marine organisms grew in daily and annual cycles that created permanent records in their calcium carbonate skeletons. By counting growth bands, paleontologists can determine how many days occurred in ancient years. The fossil record shows that 400 million years ago, during the Devonian period, Earth's year contained about 400 days of roughly 22 hours each. By the time dinosaurs ruled Earth 100 million years ago, days had lengthened to about 21 hours. The gradual slowing reveals tidal friction working consistently over vast time periods. Tidal friction between Earth's oceans and the Moon's gravity has been the dominant force slowing our planet's rotation. As the Moon raises tides in Earth's oceans, friction between moving water and the solid planet beneath acts like a gentle brake, gradually reducing rotational speed and lengthening days. The Moon has been slowly spiraling away from Earth throughout this process, gaining orbital energy from Earth's rotational energy. Early in Earth's history, the Moon appeared much larger in the sky and created more powerful tides than today. As the Moon moved away, its tidal effects gradually weakened. During the late Precambrian era, roughly 600 million years ago, Earth may have experienced extreme ice ages that temporarily affected its rotational evolution. When massive ice sheets covered much of the planet, they concentrated mass near the poles, potentially speeding up rotation despite ongoing tidal slowing. The rise of complex life forms coincided with Earth's rotational evolution in ways scientists are still exploring. The development of photosynthesis, the emergence of complex ecosystems, and the evolution of daily activity cycles all occurred as Earth's rotation was gradually slowing. Mass extinction events in Earth's history sometimes correlate with changes in rotational patterns, though establishing direct causal relationships remains difficult. Major asteroid impacts that caused extinctions also redistributed mass and potentially affected rotation, adding rotational changes to the environmental disruptions. The future of Earth's rotation extends billions of years into the future, limited ultimately by the Sun's evolution. As our star gradually brightens and eventually begins its death throes, Earth's rotational evolution will be affected by changing solar heating and tidal effects. In about 50 billion years, if no other factors intervene, Earth and the Moon will become tidally locked to each other. At that point, both Earth's day and the Moon's orbital period will equal about 47 current days. The same side of Earth will always face the Moon, ending the tidal friction that has been slowing our rotation. But the Sun's evolution will likely intervene long before tidal locking occurs. As the Sun expands into a red giant star in about 5 billion years, it will alter Earth's orbital dynamics and potentially destroy our planet entirely. The rotational story of Earth may end with the death of our star. Climate changes over geological time have influenced Earth's rotation through ice age cycles, continental drift, and atmospheric evolution. The formation and breakup of supercontinents redistributed mass around the planet, affecting rotational dynamics in ways that scientists are still working to understand. The emergence of human civilization represents just the tiniest fraction of Earth's rotational history. All of recorded human history, from the first cities to the present day, spans less than 10,000 years. During this brief time, Earth's rotation has changed imperceptibly from the perspective of human experience. Yet human activities are now influencing Earth's rotation in ways that can be measured with modern instruments. We represent the first species in Earth's history, capable of both detecting and potentially influencing planetary rotation through our technological activities and environmental modifications. The long view of Earth's rotation places current changes in perspective, while highlighting the remarkable privilege of living during the brief geological moment when intelligent life can study and understand planetary dynamics. We are witnesses to a cosmic process that began before Earth existed and will continue long after humanity disappears. As we reach the end of our journey through Earth's changing rotation, a beautiful truth emerges. Our planet's imperfect timekeeping isn't a flaw in the cosmic clockwork. It's evidence of a world perfectly designed for life, constantly adjusting and responding to the forces that shape it. Earth's variable rotation reveals a planet that is alive in the most fundamental sense. Consider what a perfectly regular rotation would actually mean. It would require a dead world, geologically inactive, with no weather systems, no ocean currents, no ice caps, and no atmosphere. Such a planet would spin like a rigid ball in space, maintaining perfect timing but supporting no life at all. Earth's rotational variations tell the story of a dynamic planet where every system interacts with every other system. When glaciers melt, they affect ocean currents, which influence atmospheric patterns, which change ice formation, creating an endless cycle of interconnected responses. This complexity is what makes life possible. The same processes that create rotational variations also drive the climate systems that regulate Earth's temperature, the ocean currents that distribute heat around the globe, and the atmospheric patterns that bring rain to continents. Earth's imperfect rotation is inseparable from its perfect habitability. Our planet's ability to change its rotation speed demonstrates remarkable self-regulation. When mass redistributes due to climate change or geological processes, Earth automatically adjusts its rotation to maintain physical balance. This responsiveness prevents runaway changes that could destabilize planetary systems. The precision required to detect Earth's rotational changes represents one of humanity's greatest technological achievements. We've built instruments more accurate than the planet they measure, revealing subtle variations that no other species could ever detect. This capability connects us intimately with our world's hidden dynamics. Modern technology depends on timing precision that exceeds Earth's natural stability, yet we've learned to work within these limitations. GPS satellites, computer networks, and scientific instruments all compensate for rotational variations, showing how humans can adapt to natural variability while maintaining technological precision. Earth's rotational story continues unfolding with each passing day. Climate change, geological processes, and even human activities contribute new chapters to this ancient tale. We're not just observers of planetary rotation. We're participants in a story that began billions of years ago and will continue long after we're gone. The mystery of Earth's recent acceleration reminds us how much we still don't understand about our home planet. Despite decades of precise measurements and sophisticated models, Earth can still surprise us, revealing new aspects of planetary behavior that challenge our assumptions. Looking forward, Earth's rotation will continue responding to changing conditions on timescales, from days to geological epochs. The interplay between climate change, ice loss, ocean dynamics, and deep Earth processes will create new rotational patterns that future generations will need to understand and adapt to. The study of Earth's rotation connects us to the fundamental physics that govern our universe while grounding us in the practical realities of living on a dynamic planet. We experience the cosmic principles of angular momentum conservation through the simple fact of daily sunrises and sunsets. Every sunset you watch represents Earth completing another rotation that's slightly different from the one before. The gentle variations in timing that fascinate scientists occur invisibly while you go about your daily life. unaware that the ground beneath your feet participates in a cosmic dance. This rotational variability places Earth among the special worlds in the universe. Most planets either rotate too regularly to support complex systems or too chaotically to maintain stable conditions. Earth's rotation falls in the narrow range that allows both stability and responsiveness. The atomic clocks that detect Earth's rotational changes will continue revealing new secrets about our planet's behavior. Future measurements may uncover patterns we haven't yet recognized or discover new connections between Earth's systems that influence rotation in unexpected ways. Perhaps most remarkably, Earth's changing rotation speed demonstrates that our planet remains fundamentally mysterious despite centuries of scientific study. We live on a world that continues surprising us, reminding us that the universe still holds wonders we're only beginning to understand. In the gentle darkness of night, as Earth continues its ancient rotation beneath the stars, we can find comfort in knowing that our planet's imperfect timekeeping reflects its perfect design for supporting the remarkable phenomenon we call life. The millisecond variations that challenge our clocks are signatures of a world that's alive, responsive, and perfectly tuned for the cosmic dance of existence. Sleep well, knowing that Earth's changing rotation is not something to worry about, but something to wonder at. Evidence that we inhabit a dynamic, living world that adjusts itself with each passing moment to maintain the delicate balance that makes our existence possible.